I made an example. I'm hoping that you already took care of the homework and you're really comfortable with the cosine of theta equal negative 1/2. So I just want to really correlate how this works and how we're going to do things. Again, graphically is not the way to go. I just showed you a graph to show you really what we're doing with this, but in reality we're going to do this using algebraically, and this is how you need to apply this in the future. The graph just helps to show. So I just want to demonstrate. If you are looking at the cosine of theta equal negative 1/2 versus cosine of 3 theta equal negative 1/2, and if I just wanted to go only between 0 and 2 pi, so if I graph y equal 1, y equal negative 1, and if I take this graph, a cosine, there is one full cycle. That is 2 pi. This is pi over 2, and this is 3 pi over 2. And if I sketch a graph of negative 1/2, I'll notice, you know what, look, there it is. And how do I do this? I'll say 1, what is the reference angle? The cosine of which angle gives me 1/2? That would be pi over 3. And where is, the second question is obviously 2. What is the cosine of theta equal negative? That happens in quadrant 2 and 3. Quadrant 2, it's 2 pi over 3. And quadrant 3, it's 4 pi over 3. That tells me that this point right here is between pi over 2 and pi, which is 2 pi over 3. And this crossing right here is between pi and 2 pi and 3 pi over 2. That happens to be at 4 pi over 3. No problem. Now watch what happens if I try to go ahead and sketch a graph of this. Let me use negative 1/2 is already labeled. It's right there. That doesn't change. But do you see the problem when I want to fit 3 periods within 2 pi? So the period for this problem, for the cosine of 3 theta, the period is 2 pi divided by 3. So by the time I reach 2 pi over 3, I have completed one full cycle. And by the time I reach 4 pi over 3, I completed another full cycle. And by the time I reach 2 pi, I fulfilled 3 cycles. Look at that. And do you see that I have 1, 2, 3, 4, 5, 6 solutions? Well, it should make sense. If I compressed the period by a factor of 3, that should take those 2 solutions and multiply them by 3, and I'm going to get 6 values. Well, the good news is the way I would do this problem is identical to the way you just finished that homework. 1 will say, what's the reference angle? That is the cosine. It doesn't matter what that angle is. How would that equal 1/2? That's pi over 3. Nothing changed. 2, we would say, where's the cosine of any angle negative? That would be in quadrant 2 and in quadrant 3. Well, guess what? In quadrant 2, it's 2 pi over 3. I'll leave some space. Quadrant 3, it's 4 pi over 3. Now, so that I don't have to figure those out by hand and end up spending a very long time trying to see where those are, all what I have to do is add the period for sine and cosine. The period for sine and cosine is 2 pi k. For tan and cotan, pi k. Now, I know the period is not 2 pi, it's 2 pi over 3. That's okay. The way we're doing this, the only time 3 theta ever comes in, it at the very last step. This is where we set 3 theta equal. And we said when you're dealing with fractions, you don't divide by 3, you multiply by a third. If I multiply all of these by a third, guess what? Guess what this got me? At theta equals 0, that tells me this is 2 pi over 9, and this is 4 pi over 9. And if you add a period, which we agreed was 2 pi over 3 right there, if I add a period, I will get the next time that happens, and the next time that happens. And if you take 4 pi over 9, which is right there, and add a period, you'll figure out when that happens again and when that happens again. I should have made that graph bigger, I'm sorry. But we're not going to graph. We're going to solve using algebra. And we're going to proceed the same way we did the homework that you just submitted. The only difference, at the very last stage, we're going to have this 3 theta added in, and we're going to add 2 pi k, which is called the general solution. The general solution is basically finding all the solutions. And that's how we're going to proceed. Otherwise, it's a lot of work for me to figure out by hand, when do I get 2 solutions, when do I get 3 solutions? Well, this case, I'm not going to worry about it. Let me tackle a problem from the book. Let me look at problem number 30. So continuing where we left off. 1, I need the reference angle, and in case you missed it, this is for like, I don't know, not third time, this is like the 30th time will be a charm. The tan of which angle gives me 1, positive 1 pi over 4. 2, where does tangent negative? Now the good news about tan and cotan, you could proceed like we did, not a problem. You could do this. You could say tan is negative in quadrant 2 and quadrant 4. The deal is, if you take a tangent, any angle, and add pi k to it, you'll get the other angle. And that's a property of tan and cotan. That's not true for sine and cosine. So for now, I'm going to ignore that so that you wouldn't be confused. I'm going to say, what is pi over 4 in the second quadrant? 3 pi over 4. And what is pi in the fourth quadrant? 7 pi over 4. Now, if this happened to be just a theta, I'm done right there. But I noticed they really compressed this. I'll add the pi k because I don't want to really guess what those are. And I'll notice the very last stage of this problem is where the angle comes in. And now all what I have to do is multiply by a half. And what do you notice will happen? If I multiply by 1/2, I will get theta to equal 3 pi over 8 plus pi over 2k. And or theta equal from this piece 7 pi over, that's a 4, 8 plus pi over 2k. So I'm doing all the work algebraically. If I was to ask you what's the period for this, wouldn't you say the period is pi divided by 2? And look, that's not a coincidence. The algebra matches. And now, I remember on this problem they wanted the solutions between 0 and 2 pi. So guess what? All what I have to do is let k equal 0. I'll get theta to be 3 pi over 8 and 7 pi over 8. That's allowed. K equal 1. If I take 3 pi over 8 plus pi over 2, that would be all over 8. That's 7 pi over 8. And here, if I take 7 pi over 8 and I add pi over 2 to it, 7 pi over 8 plus pi over 2 times 4, that is 4. That's 11 pi over 8. That's also allowed. Now, if you are wondering what do I mean by that's allowed, I want to run theta between 0 and 2 pi. So 2 pi, if I want to make that over 8, that's 16 pi over 8. That's allowed. So if I proceed and let k equal 2, I'll notice I'll get theta to be, and look how this is playing. I went from 3 pi over 8 to 7 pi over 8. I added 4 to the top. If I add another 4, isn't that 11 pi over 8? Right? And here, I went from 7 to 11. I added 4. If I add another 4, 15 pi over 4, that'll work. And where did we see this? We saw this when we sketched the graphs of sine and cosine, and we labeled those 4 main points. If I let k equal 3, I will notice that theta will be So if I add another, so basically this is how it works. I went from 3 pi over 8 to 7. I added 4 to the top, add another 4, and add another 4. And do you notice what's happening? And if I add 4 here, that's 19 pi over 4. That's bigger than 2 pi. Remember, 2 pi, if I want to make it over 4, if I want to make it over 8, did I say 4? I meant 8. I'm sorry, you guys. If I want to make it over 8, isn't that 16 pi over 8? So, there it is. Do you notice that 7 pi over 8 is right there, 11 pi over 8 is right there, and 15 pi over 8 is right there? This only happens with tan and cotan. So if I take 3 pi over 8, the very first, and the 7 pi over 8, and the 11 pi over 8, and the 15 pi over 8, I'll notice all of these are repeating in there. And that happens always with tan and cotan only, because if I was just to take one of the angles plus pi k and not use the other, that'll work. Because tangent has a period of pi and it repeats every pi or 180 degrees ratings. You could do that for tan and cotan. That doesn't work on sine or cosine. Let me do another problem. So if I pick a problem like number, well, something deformed. Okay, 32 would be deformed. That would be not your standard graph. Well, graphically, this is a lot of work. Algebraically, we should be able to get this very quickly and efficiently. Let's see. 1. What is the reference angle? That is the tangent of which angle gives me, the cotangent of which angle gives me a radical 3. That would be a reference angle of pi over 6 or 30 degrees. 2. Where does the cotan of an angle, any angle, is negative? That is either in quadrant 2 or 4. Well, guess what? If I just picked 2, and I say here, of course, in quadrant 2 it is pi over 5 pi over 6, and in quadrant 4 it's 11 pi over 6. But if I just say, you know what, let's take 5 pi over 6 plus pi k, that's sufficient only for tan and cotan. What equals that? The angle. This is the first place where we use the angle algebraically. If I multiply by 3 halves to really solve for x, I'll get theta to be 5 pi over 4 plus 3 pi over 2k. And here I let k equal 0. I'll get theta to be 5 pi over 4. That's accepted. K equal 1. I'll get theta to be 5 pi over 4 plus 3 pi over 2. And that turns out to be all over 4. That's 11 pi over 4. That's too big. So I only get one solution for this problem. That's it.